Hello, everyone, and welcome to our webinar today. The topic for today's webinar is use of operating agreements and energy storage to reduce photovoltaic interconnection costs. This webinar is being presented by the Clean Energy States Alliance, also known as CESA, and we have a really exciting group of speakers on the line today to talk with us. Before I pass it over to them, I'd like to give you a few quick webinar logistics notes. All of our attendees are in listen-only mode. You have a couple of options to join the audio portion of our webinar today. You can call in via telephone, or you can connect via your computer mic and speakers. If you'd like to minimize your webinar console so that you can view the presentation more fully, you can click on the orange arrow that you see circled here, and you can also click on that arrow to expand your webinar console. And one thing that you might like to do with your webinar console is to submit your questions and your comments. We'll be saving about 15 minutes at the end of our webinar for a Q&A with the audience, and we want to hear from you. We want to get to as many questions as we can, so please do type those questions in when you think of them, and we'll get to as many as we can. A final note, yes, we are recording this webinar, and we'll email you probably tomorrow with a copy of the slides and the webinar recording. And we'll also post those webinar materials on our website at cesa.org/webinars. So with that out of the way, I'll now pass it over to our moderator for this webinar, Todd Olinsky-Paul. Todd is a Senior Project Director here at the Clean Energy States Alliance, and he will get us started.
Great. Well, thanks everybody for showing up, and welcome to the webinar, and thank you, Samantha, for the introduction. I will do a very brief intro here of CESA, and then I will introduce the speakers. We have a power-packed panel here of folks to explain this very interesting and very pertinent topic. So first of all, for anyone who doesn't know, Clean Energy States Alliance is essentially a membership organization. We're a nonprofit, and the members are state clean energy agencies. You can see many of our members' logos here on the screen. We help our members with whatever they need in the realm of clean energy policy and program development, research, and so forth. The next slide, please. And so, Samantha, if you could just advance that. Hey, thank you very much. So, as I said, we have a number of very excellent speakers today. And I will very briefly go through and introduce them, and then they will introduce and discuss the topic. After the presentations, we will, of course, address as many of your questions as we can. We try to set aside time at the end of every webinar to do that. So as we go along, if something occurs to you, a question or comment, please just go ahead and type it in. Don't wait until the end, and that'll help us to kind of organize those and get to them. So today, we will be hearing from Carrie Gill, PhD, Chief Economic and Policy Analyst at Rhode Island Office of Energy Resources. Dr. Gill has over a decade of experience in the energy and environmental fields. She provides strategic oversight of Rhode Island's clean energy and climate policies and programs, chairs Rhode Island's Green Building Advisory Committee, and serves on Rhode Island's statewide Planning Council Technical Committee. We will also hear from Joyce McLaren, an NRL researcher and V-Market research analyst. She joined NRL in 2009. Joyce works on a wide variety of topics, including solar market analysis, residential and commercial solar and storage, electric transportation, and grid interactive buildings. And she scopes and provides analyses and technical assistance to utilities and electric cooperatives, as well as state energy offices, public utility commissions, and municipalities. We also have today Dr. Naeem Dargouf, researcher in the Electricity Markets and Policy Department at Lawrence Berkeley National Laboratory. Naeem conducts research on renewable energy policy and economics, examining the relationships between distributed energy markets, retail electricity rate design, and customer economics of renewables. Naeem has been the senior economic expert on U.S. national lab teams providing international institutional support in 8 countries on the financial impacts of distributed solar to governments, electricity utilities, and regulators. And we will hear from Ryan Constable, a distribution planning manager at National Grid, one of the major electric utilities in the Northeast. He has over 25 years of utility experience, mostly focused on distribution systems. His team currently focuses on long-term planning and load and generation interconnection studies. In addition, we will be joined by two people for the purpose mostly of fielding your questions, in addition to the speakers, who will also be doing that. So the additional folks we're being joined by are Shauna Beeland, Administrator of Renewable Energy Programs at Rhode Island Office of Energy Resources, and Sydney Forrester, Scientific Engineering Associate working in the Electricity Markets and Policy Department at Lawrence Berkeley National Laboratory. Shauna works on a range of initiatives at Rhode Island Energy Office related to renewable energy programs and policy, such as implementing solar PV, energy storage and community solar programs, ensuring renewable energy quality assurance, designing new programs to improve solar access on previously disturbed lands, and increasing solar access among low to moderate income customers. And Sydney focuses on renewable energy adoption and new utility business models. Specifically, she studies both the quantitative and policy-driven aspects of distributed PV solar adoption, as well as the impacts of distributed energy resources on utilities and ratepayers. So, if you could advance the slide, please, Samantha. Those are our speakers and experts for the discussion today. And I will now turn the microphone over to Carrie Gill to kick off our presentation.
Thanks, Todd. Thanks, Sam. And thanks to everyone at CISA for hosting us and for your participation in this project as well. We really appreciate your expertise here. First of all, I want to say how impressed I am that 200 folks are here in attendance despite the technical nature of this presentation today. So thank you for bearing with us. Throughout, we're going to have information that might be of interest to you if you're a distribution system planner, an electrical engineer, if you're interested in legal and regulatory affairs, if you're interested in economic analysis. We've got a little bit of everything for you. So for this project, we're going to be talking about something that became a concern in Rhode Island, and we wanted to address it. We have been hearing at the State Energy Office concerns from developers about really long interconnection timelines and really high interconnection costs, particularly for standalone megawatt scale solar PV located in the rural portion of our state along radial feeders. And so we're trying to brainstorm different ways to address this issue. And instead of just having the developers incur and the customers incur those high costs, those time delays, or downsize or forego the project altogether, we wanted to understand the role that energy storage could play in helping to alleviate those interconnection costs and time delays. Next slide, please. We applied to the Solar Energy Innovation Network, which is a fantastic program supported by the U.S. Department of Energy. We got together a team of experts ranging from folks on the policy side at the Office of Energy Resources, the technical side at the National Renewable Energy Lab and Berkeley Lab, the utility perspective. So we had a whole team of folks from National Grid, and then we relied on folks from the Rocky Mountain Institute to provide facilitation support and project management. The Clean Energy States Alliance really helped us out with helping us connect to stakeholders like we're doing here on this webinar today. And so we thank them so much for their participation in this program, and we thank the Department of Energy for their support. Next slide, please. In this presentation, we're going to be referring back pretty frequently to what we're calling an operating envelope agreement. So I just want to get this out of the way before we get started. An operating envelope agreement is what we're defining as a contractual agreement between the utility and the system owner that defines a mutually agreeable set of time-based technical operating requirements. We're calling this an operating envelope. These operating requirements are for a PV and storage combined system that limit risk to neighboring customers as well as the utility's infrastructure. And these parameters should also provide certainty to both the utility and the PV system owner. So we'll come back to this definition later, but no surprises here, no suspense. This is what we're talking about. We've published 2 reports that are available at the National Renewable Energy Lab's website and at the Office of Energy Resources website. We'll have links for those later in the presentation. So if you want all of the technical details, please do go there. We have a limited amount of time to talk today, and so we'll keep things at a high level and we won't go into those details unless we have questions. We're going to have a range of speakers today. First, we'll go to Joyce, who's going to talk a little bit more about the context for this and the technical analysis. So is energy storage even technically viable? And then we'll turn it over to Ryan, who's going to talk a little bit about the terms and conditions. So what do you need to include in that agreement to limit that risk and provide certainty? And then we'll turn it over to Naeem, who's going to talk about the economic portion. So does this even make economic sense? When does it make sense? What's the payback like? What are the factors that go into that? We'll conclude with some next steps. So if you want to take this back to your policy office, your utility, your regulator, and talk about it, we've got some next steps for you to consider that. With that, let's go to Joyce for the technical analysis. Next slide, please.
Thanks, Carrie. Hi, everyone. So as Carrie was saying, the overall goal of the project was to identify options that manage the interconnection costs and timelines for DG projects that are not connected to a load. So DG projects, solar projects that are connected directly to a distribution feeder in front of a customer meter. So these projects, in the case of Rhode Island and in other places across the country, are increasingly triggering violations under certain circumstances. So a couple of the circumstances that where we're seeing increasing number of solar systems causing violations on feeders are during months of the year when PV generation is quite high, but load on the feeder is low. So in this very simplistic graphic, you can tell that PV generation is higher in the shoulder months in the spring and the fall, but load during those months is quite low because maybe there's not air conditioning load or heating load as much during those months. So this is one instance where a feeder, there might be violations triggered by a solar system. On the next slide, we're going to zoom in to a particular day and look at the hours of the day in which violations may be triggered by increasing amounts of solar on a feeder. And here you can tell that generation, solar generation is happening mostly in the middle part of the day, but on this residential feeder, load is quite low during that time of day. So we might see violations during these times of day. So what we were doing with our technical analysis was exploring options for mitigating these types of violations throughout the course of a year. And there's a number of different ways that they can be mitigated. You can, for one, downsize the solar system in order to reduce the risk of violations. That option is not always preferred because we have renewable energy goals that we're trying to meet. And so larger solar systems may be preferred in some cases. We can also curtail solar, which also may not be preferred in some cases for the same reasons and for economic reasons. Or on the next slide, let's jump to the next slide, we can add battery, and increasingly this is an interesting option. So the technical analysis was looking at all of these different options, the curtailment, the downsizing, and the adding of battery, to see which of these options are feasible in any particular case and to negate the violations, and then how much, what's the economic impact across the different options. So let's go into the next slide, which gives an overview of our analysis method. So basically this simplifies our method a bit. We first wanted to identify grid violations, which included things like over voltages, under voltages, line overloads, transformer overloads on an example feeder. Then we wanted to look at different options for mitigating those violations. Those that I covered, including infrastructure upgrades, reduction in PV size, curtailment of PV, and the addition of battery storage. And then from that, we wanted to understand what the technical parameters would be of an agreement between the utility and the developer that would ensure that the violations are mitigated, and that the developer understands the operating parameters that are needed in order to mitigate the violations, but still have the economic benefit of the system that they are expecting. And then these technical parameters are going to feed into our economic analysis that compares and weighs the options, but it's also going to feed into the terms and conditions of that agreement, that OEA, the operating envelope agreement between the utility and the developer. So the next slide, please. So to conduct this example analysis and demonstrate the methodology, we just chose an example feeder. We used an IEEE feeder that's open source. The data is all open source. We chose a representative solar generation profile and a representative load profile from a residential feeder. And this was just to demonstrate, again, the methodology that could be used to develop these operating parameters. So we first identified the violations using an 8760 time series simulation in OpenDSS Direct. We can certainly provide more information about the specific model that was used, and I will say that model has recently been released on the NREL's GitHub site and is available for everybody to use, and we can certainly provide information about that. But we used OpenDSS Direct with an open source Python wrapper to conduct this time series analysis on several different scenarios. And let's go on to the next slide, which shows the different scenarios. Well, these are the metrics here of the output from the time series analysis. We were looking at voltages, we were looking at loading, line loading, the number of violations that were occurring in any month, and the by hour of the day. So these are all the different metrics that were coming out of this time series analysis. And if you go on to the next slide, it shows the scenarios that we were looking at. Again, we were looking at the originally proposed PV size, both with and without smart inverter controls, a downsized PV size, and then we were exploring this option to add a battery and what that would do in terms of mitigating violations. Next slide, please. So basically the result of running all these different scenarios and looking at every hour of the year, how to mitigate all the violations over every single hour of the year, we can boil the result down into this heat map, which is a maximum allowable export or injection level for every hour of the year across for one single feeder across an entire year. And these results, this table, is basically the table that would be inserted into an operating envelope agreement, which is that agreement between the utility and developer, to define what the parameters are for operating a specified DG system on a distribution feeder. This is also the information that was fed into the economic analysis that our colleague Naeem will talk about here in a little bit, that helps to weigh the different options economically from the developer's perspective to select which one is preferable from their perspective. So next slide, please. I believe this is the last slide that I'll be introducing, and it's just really to point out that there's a lot of different variations of this heat map or this operating envelope agreement that can occur depending on the context or the where the feeder is and what's going on in that specific location. It might be a very simplistic OEA. The parameters might be quite simplistic. It could be that the enforcement is the same across the entire year. and that the enforcement may be the same across a complete day, all 24 hours of the day. The enforcement type is the same. It could be that the magnitude of the violations are really large at certain times, at certain times of the day, and so you're requiring zero export during a particular hours. Or it could be very nuanced. This agreement might be really complex and really nuanced, depending on how detailed the stakeholders want to get in the formulation of it. You could vary these parameters over the course of a month or over the course of the day. You can have different maximum export limits in every hour, basically every hour of the year, if you really wanted to, if you wanted to manage it that way. So this is just to make that point that it's up to the stakeholders and it's up to the context of the situation of how you want to design the OEA parameters. So I'm going to pass it back to Carrie.
Thanks, Joyce.
Hey, let me just jump here for a second, Carrie. This is Todd. Because we have a question that I think is really important for people. I don't usually interrupt in the middle, but can somebody speak to, when you talk about violations, what does that really mean? Is that a contractual violation? Is it violating the laws of physics? Is it making the grid unstable? What are we talking about, right, and why is it important?
Yeah, thanks for that, Todd. And that is really important. And in this context, we're talking about violations on a distribution feeder. So line overload, voltage violations. So these are violations that can cause outages, basically, on a distribution feeder. So it's a physical thing. It's not a contractual thing.
Todd, any other questions before we move on? Okay, hearing none, thanks, Joyce. So what Joyce just went over informs the first half of the operating envelope agreement, which is the technical requirements. So what does the paired energy storage system need to do in order to mitigate those violations and allow the full-size solar PV system to be installed at lower interconnection costs and potentially quicker? If we go to the next slide, the second half of the operating envelope agreement is related to the terms and conditions. Sam, can you go to the next slide, please? Thanks. And so for the terms and conditions, this is really the critical component that can limit the risk and provide certainty. And specifically what we heard from developers through focus groups is that having financial certainty, so being able to project your revenues, is absolutely critical for even considering entering into an agreement like this. So these terms and conditions were designed with both input from a developer focus group. We thank everyone that participated in that, and from some developer advocacy organizations, and then also in line with discussions that we've had with National Grid, the utility. As we've presented this before, a lot of folks say, wow, you have a utility on board. Yes, we do. So Ryan will walk through the terms and conditions that we've laid out here. There's a lot of open ends, but we try to give pretty good guidance for what you need to consider when coming up with something like this. Ryan, it's all yours.
Okay, next slide. So performance validation is an important topic for a utility, just because we're the managers of the safety and reliability for the electric system. So we need to make sure that all the system resources are operating appropriately, so that they avoid those violations that we just talked about. So when I talk about these topics, I'm going to raise concepts, and then I just want everybody to recognize that no decisions have really been made. Right? This is a sort of a complicated idea, and the performance validation is complicated in its own rights. So when we talk about performance verification, right, and we'll start from one end of the spectrum, is simply we let the operating agreement, the legal document, be basically be the device that we all rely on, right? And of course, this makes the utility, out of all the possible options, this makes the utility the most nervous. And so we just say, hey, we have this operating agreement. We're going to trust that you're going to operate within it, and then we'll sort of operate the system a little bit blind, right? Then you can move towards some cursory monitoring and alarms, where you basically see the violation after it's happened, right? And then of course you would call up the specific site and you would work through the violation with that specific site. And again, that's a little bit better, but again, it has concern for utilities because the violations actually already happened. And then of course, the last one is to actually install protection systems and monitoring systems, so that if the violation is about to happen, a protective device takes action and takes the site offline or curtails some asset on the site in some manner. And of course, that last one is the one the utilities like the best. And so there can be differences in how we apply these performance metrics as well. And where there can be differences is in what the sites actually want to do, right? So if a site is just going to operate their system to avoid a system constraint that the utility is very aware of, and has studied it in depth in their interconnection study, then I think there's a simplified sort of monitoring and oversight and compliance path there. However, if the site wants to participate in various wholesale markets, which go beyond the local system constraints, such as a regulation market where there can actually be significant ramp up and ramp down of sizes in very short periods of time, which can result in flicker. Those type of things might require more compliance oversight. So there's a lot of talk going on right now, right? This is happening. This is changing every day. This is changing while we were developing this presentation, right? Just to tell a quick story, right? We had a conversation yesterday on how to do compliance on a site for a customer who had kind of a complicated application requirement, and we went through those various items. Do we trust them to operate on their own? Do we need to have some sort of oversight? Where do we need to backstop a protection system, right? So this stuff is happening and changing every day very rapidly. Can we go to the next slide? As far as the terms go, again, this is something that the utility needs to proceed cautiously on, but we understand the need for it, right? So we understand that these systems, like a PV system, is approximately 20 years, and a battery system might be 10 years, right? And that's just the utility understanding of those lifetimes of the systems. Of course, things could actually be very different based on how an applicant determines their own economics. And we understand that when you have an interconnection services agreement, that there needs to be some financial certainty behind that agreement, so that these projects can survive their own economics. So we understand all that, but at the same time, we're locking into an agreement that can possibly put handcuffs or some requirements on our system, right? So we have to find that balance between, making sure that these systems and these applicants can financially proceed with their projects, and then managing a system that can change. So we know things are going to change. A utility has to reconfigure the system for reliability reasons. There might be load growth reasons, and we see things like vehicle electrification and heating electrification on the horizon, right? When that happens, everybody's going to be competing for generation capacity and load capacity on the system, right? So, we have to be careful about how we manage these operating agreements as the system changes over time. So, there's basically three ways, right? The utility, we can require a change, right? And these are ideas, these are concepts. We would be able to require a change if there's non-compliance, and we probably wouldn't really require a change. We would more require compliance, but I could see that in extreme cases we change the OEA. The utility can also request, like I said before, the system has changed for reliability reasons. The system has changed because of some sort of major load shifting. We can request a change. Of course, we know that when we request a change, if it's not in the developer's best interest, they're going to say, no, I want my original OEA. I want my original ISA. And then the last thing is the customer, of course, can request a change. Maybe different wholesale markets develop. Maybe a distribution market emerges in the future. We know that we have distributed energy resource management systems on the horizon for the New England area, and when those occur, there most likely will be better operating envelope opportunities, meaning an operating envelope would still likely be required, but it would be less restrictive, because again, the DERM system is managing the system on a real-time basis. So and so those are basically the three options of how it would change. Next slide. All right, so now what happens for non-compliance? I'm just going to do a quick story. In another jurisdiction, we had a developer, didn't have an OEA, but of course had maximum export requirements, maximum megawatts that the site could generate onto the system. And when we study these, right, the generation export is right up against our summer limits or our system limits. We found that the site was exporting higher than their ISA allowed. And the good part was we found it in the wintertime when load was actually a little bit lower. And then we actually have different winter ratings. So the ratings are a little bit higher. So it didn't damage the system. It didn't create an issue, but it would have during the summer period. So we disconnected that customer, and then we worked with the customer to resolve their specific issue. We set them at, we actually changed the protection system so they could only operate at about 85% of maximum export. And so we did that until they could basically reset their system and reset their controls so that the violation wouldn't happen anymore. And then we relax our protection system so they could go back to 100% output. And they were out for, they were out for a few weeks while we figured out the system. Then they were on their 85% limit for a few months before they could get their control system back online. So this can, be sort of a substantial amount of a substantial period. And then there's a question of liability for damages, right? So now, should this be in the OEA? Should this be in the interconnection services agreement? Hey, if you violate your operating envelope and you actually damage the system, do you pay damages, or how is that going to be assessed? Again, we don't have that completely figured out, but of course the utility wants that protection, right? So, in essence, like a compromise for sort of offering this this operating envelope, which is it does create some risks, right? It does create some concerns. We have to be honest, right? And so because of those concerns and because of those risks, what happens if they occur, and then who's going to pay for them? Dispute resolution, of course, is a big topic. And so, yeah, again, we'll just have to see, right? So, again, it's not completely figured out, but there will have to be a dispute resolution process set up. And we have test cases right now on dispute resolution around ISAs, right? And of course, it's incredibly protracted, a very legal process, and takes a lot of resources and time. And so I know we'd all like to avoid any dispute resolution, but we do have to consider one if we move down this OEA path. Next slide. The last thing that the utility is concerned about is changes in ownership. So we see this a lot, where a developer will proceed through an interconnection study, complete the interconnection services agreement, and then sell the project off to another developer or another financial institution or another owner. Often that new owner does not understand the implications of the interconnection services agreement in the first place, right? For instance, the new owner often comes to us and says, I want to change the size of the photovoltaic system. I want to change the size of the battery. And they don't understand that that actually means the ISA is thrown away and they have to reapply and they have to go to the bottom of the queue. And so we're dealing with that a lot, where these changes in ownership happen and it creates kind of a churn and some uncertainty. So because of that, we need these OEAs to survive any changes in ownership, and then we need to even ensure that the contact people are carried through. So if you are going to change ownership, you have to let the utility know who the new contact person is, so that we can actually have the OEA implementation, compliance, verification. What happens if a violation happens, right? We have all that stuff set up ahead of time, because there are cases right now where our operators have to contact a distribution generation site and the ownership has changed and the contact doesn't work anymore. So that's occurring right now, even without an OEA. So that's basically it for me, Carrie.
Thanks, Ryan. Really appreciate it. So I know Ryan just raised a whole lot of questions, and I'm sure everyone else has questions too. We describe a lot of this and a lot of these considerations right in our report, so I'll refer you to that later. Also, the key thing here is that a utility's interconnection services agreement may already have a lot of this information that can be adapted. And so the interconnection services agreement and the operating envelope agreement can really become one. We'll talk more about that in a second. Let's flip to the next slide, and Naeem will actually go through, now that we know that we can have this contractual setup, we know that this is technically feasible, what are the actual economics associated with doing this method?
Great, thanks so much, Carrie. So now I'm going to be walking through the analysis that explores how the operating envelope may impact the economics of a solar project for a developer. So as we know, the OEA gives developers more flexibility in deploying solar in distribution feeders that are nearing their hosting capacity. As long as the operating envelope is adhered to, the developer can really size and operate their system as they wish. In the economic analysis, we look at the economic impact of the operating envelope, taking the developer's perspective. So we simulated the expected revenue and cash flow for a developer looking to install solar on a solar constrained distribution feeder in Rhode Island. So this is a specific case study that we're looking at, though I'm going to be focusing on kind of what is broadly applicable here. We use the technical specifications in the operating envelope from the technical analysis that we've already covered in our example case. So we consider 4 options for the developer. The first is a downsized PV system. So the developer may have originally proposed a larger PV system, but to avoid grid violations, the PV system is downsized to a smaller size. The second is where developer may install the originally proposed size, so the larger PV system, but pays an infrastructure upgrade cost that would mitigate any grid violations associated with the PV system. So that's kind of the business as usual case. The third is where the developer installs the originally proposed PV system and agrees to adhere to the operating envelope and therefore doesn't need to pay these interconnection costs, but manages their PV system and adheres to the operating envelope by curtailing solar and hence just losing out on revenues at times. And then the final option, option 4, is where the developer is really installing the original proposed larger PV system and agrees to adhere to the operating envelope agreement and does so by charging a battery and or curtailing PV during the hours when PV generation is above the specific specified limits. And that we consider kind of a number of different battery sizes. And for the last option, we're optimizing dispatch using a linear optimization model that we've implemented in MATLAB. Next slide. So here are a few of the underlying assumptions that we use to be able to compare each of the options, which all have very different cost structures. So the smaller PV system size for option 1, larger for option 2 through 4. Storage, we're looking at a variety of different storage system sizes, and I'll let you go through the rest offline in the interest of time. Next slide. So on this slide, I'm showing an example of how one might dispatch a battery storage system for option 4, where you have a larger solar system plus an operating envelope agreement, as well as a storage system. It's the one that's the most complicated case operationally. The other options are really more simple. So let's look at this figure in more detail. Again, this is the operation of a solar plus storage system that's dispatched to maximize revenues while abiding by the OEA. The yellow line shows the output from the PV system. The solid blue line is the maximum allowable export as per the OEA. The pink bars show how much electricity from the PV system is exported to the grid each hour. The shaded blue shows how much electricity is curtailed given the capacity limits of storage system. And the red bars show how the storage is charged from the PV system, and the purple how they're discharged from the storage. And the dotted line is just an indication of the wholesale market price, basically how much the developer has paid for any electricity that's exported to the grid. So first thing we see is that exports from solar and storage are never higher than the blue line. So that's good. That means the OEA is not violated in any hour. During the hours when PV generation is higher than the OEA limits, solar is either used to charge the battery or curtailed or both. On this particular day in March, the price starts rising after 4 p.m. into the early evening. So during those hours, solar is exported as much as possible, and then the battery maxes out its discharge to benefit from those higher priced hours. Option 4, so this PV plus storage option to manage the OEA, is only economically feasible if the additional initial cost for storage is offset by this type of price arbitrage that we see here, where storage is charged during the low-priced hours and discharged during higher-priced hours, hence maximizing revenue. And those initial costs, of course, means that in terms of CapEx, the option of PV plus storage is going to be the highest, or at least higher, and that, of course, will depend on the size of the battery. So we look at CapEx of each of the options in the next slide. So in this figure, we look at the initial cost of the 4 options using our input assumptions. The lowest cost is the first, the downsized PV system. Of course, the PV system is smaller in that case. The second option, we have a larger system, but we also have what can be a significant interconnection costs associated with that larger system in that second bar. In the third option, the developer pays only for the larger PV system, no additional upgrade costs because they're curtailing and therefore abiding by the OEA. The last 2 bars are for the fourth option with 2 different storage system sizes. Of course, cost is only half the picture. We also have to consider revenues, and that's what we look at in the next slide. So here we see the revenues for the first 15 years of each of the options considered. The first bar is option 1, the smaller solar system. Here, the revenue is dependent on the wholesale prices and PV generation profile alone. It has the lowest revenue. It's a small system. The second bar, option 2, is that larger system with infrastructure upgrade costs. No curtailment is necessary because the developer has paid for the larger upgrade costs. The yellow bar is option 3, where you have a larger PV system, but you are curtailing in order to adhere to the operating envelope. So you see here that you have a much lower revenue each hour, especially compared to when you're not curtailing, of course. The OEA in this case curtails the PV system just about 1/3 of the time. The last 2 bars are for option 4, the larger PV system with a battery and curtailment to adhere to the OEA, storage, of course, increases the revenue as compared with option 3, depending on the size of storage. Storage avoids the need to curtail that electricity and so creates value by then discharging later in the day, especially when prices are highest. And so there's also an arbitrage element to that as well. You'll notice that the annual revenue from the PV plus storage system that adheres to the OEA is greater than the annual revenue from the larger PV system, but that is only true for the first 10 years. After that, we assume that the battery is retired, and therefore you have kind of that much lower revenue after year 10. So next slide. So if the developer chooses option 4, where you have solar plus storage to manage the OEA, they're going to have to choose what the right storage system size is. The basic idea behind this figure is that the smaller the PV system, the smaller the storage size, the more PV generation is curtailed, since the storage is limited by capacity in charging any given hour. And so you also see a diminishing returns here. Next slide. So here we're showing the break-even costs of the storage system, which are highest for the smaller storage systems related to the previous slide. So correspondingly, the incremental value of storage is highest for smaller systems. And this is partly due to the fact that those systems are more efficient at avoiding curtailment, and there's more efficiency in arbitrage. So we were showing these trends to understand some of the dynamics and choices that developers need to make rather than payback times or rates of return, because those are going to be highly dependent on the input assumptions, how the OEA is defined, the wholesale electricity prices, and capital costs. The OEA and wholesale electricity price profiles are really going to be very location dependent, and capital costs are declining significantly over time, particularly for storage. We did look at a number of sensitivities to try and understand how various levers impact some of the results that we see. In the interest of time and to allow time for questions, though we do have that in the next slide, we will go ahead and move forward, and I'll let you review this offline.
Thanks so much, Naeem. And you can go ahead to the next slide, Sam. So one of the key innovations of this work is that this allows the ownership and the management of the system to be retained by the system owner, as opposed to relinquishing that control to a utility. This is an entire paradigm where it is not the utility controlling the system, it is the system owner. We saw that be put into place with both the technical requirements for the operating agreement and the terms and conditions to make sure that everyone's on the same page and to ensure that we're limiting risk and providing certainty. What we just saw from Naeem's analysis is that from a policy perspective, what this does is it allows us to internalize and monetize another value that energy storage can provide. Energy storage can provide additional revenue, it can decrease interconnection cost, and importantly, in some instances, it might be able to decrease interconnection timelines as well, which is what we've heard is really important for developers. We leave it up to developers based on their specific technology portfolios, their soft costs, their markets. We leave it up to developers and utilities to figure out what makes sense for them and what's right for them. So if you wanted to take these concepts back and talk about them and adopt them in your own state or at your own utility, we suggest definitely including a multiple perspective collaborative stakeholder group to talk through these things. You can start with your utility's ISA, and then you can crosswalk the terms and conditions from the operating envelope agreement. As Joyce said, some of the models are open source and available online. You can read the report, see what that modeling looks like to do the technical analysis. And of course, we're always here if you want to reach out to us as well. We suggest doing this well in advance of any potential update to your interconnection tariff so that you can include these considerations in your interconnection tariff. And we also recommend having a sample agreement beforehand so that everyone knows what you're working from and what to expect. That will ensure that this is actually impactful. And then along with that too, Definitely specify the process. Who does what and when? How long is it going to take? What are the conditions? What are the contingencies? What are the outputs? We discussed a little bit more about this in the report. Next slide, please. In looking across the United States, we didn't find anyone who is already doing this already. If you are, please email us. And if you decide to move forward and implement something like this, please also let us know. There's an email address here. There's a few email addresses in the report. We want to hear from you about this. I know we're short on time too, so you can also use this email address if you want to follow up with us offline with any questions that you have. Next slide, please. The citations for the reports are here. Please go read them if you want full details. The whole team's here to answer your questions for another 10 minutes, and thanks so much for your time today.
Great, thank you. And thank you to all the presenters. If you could all turn on your webcams, and those of you who are on hand for questions and didn't necessarily present also could do that. We're still going to need the slides up, Samantha, because we have a question about Joyce's heat map. We have a couple of questions actually about that. And I wanted to get those out of the way because I'm not sure. I think people looked at that and said, a couple of people looked at that and said, why does the heat map have higher export in the months and hours that it does? And is that a real world representation? And are those months actually accurate in terms of higher allowable exports? So if we could pull that up and just kind of get that out of the way.
Anyone have a slide number for that?
It's the one with the
down.
red, orange, green.
11.
Like a table.
There you go. Okay, so it sounded like the question was, is it representative?
Yeah, some people felt that the months where you're showing the highest allowable exports are weird months to be, that they're not when the solar is mostly generating. And just, if you could just explain a little bit more, is this meant to be accurate?
So this is our one case study example. So this is based on the example IEEE feeder that we used along with a very specific solar generation profile and a specific distribution feeder load profile. So this, if you go to the technical analysis, the report that was linked there on Carrie's last slide, it will give all the details of the analysis and all of the inputs that that we used and links to those. They're all open source data, so you can go back and take a look at what they were specifically. But this is just based on one case study. It was designed to demonstrate the method. It wasn't designed to be representative of a broad spectrum of feeders across the country or generation profiles across the country. It was just designed to demonstrate the methodology. Does that clarify?
Yeah, I think that does. And I'm sorry, I don't mean to interrupt you. I'm going to try to get a few of these questions in the time we have remaining. So next one is, could somebody talk about how the OEA parameters might be set in the context of a feeder that's likely to see multiple proposed PV projects? So in other words, would you expect the first project to receive the most favorable OEA with subsequent projects getting greater restrictions? Or how does that work?
I'll start off with this, and then I think Ryan and Joyce probably will want to chime in. So the whole concept here is that the operating envelope agreement is sort of treated in a similar way to putting together an interconnection services agreement, where it's sort of first in gets that part of the feeder. And so we have no reason to treat this any differently in the absence of additional either statutory or regulatory direction. Ryan, would you like to add to that?
Yeah. So just echoing that statement, right? So just the way the rules are currently, right? The first person gets the capacity, right? So you would create an OEA for that first applicant. Then if there's a second applicant on that feeder, their OEA would have to consider the first site's OEA. So the second OEA would of course be more restrictive, right? And the third OEA would be even more restrictive, right? So it would compound over time.
Thanks, that's very helpful. Here's a question for Naeem. The question is, does Naeem's energy storage revenue assumptions include any capacity reduction revenue? For example, through the Connected Solutions program in Massachusetts or other similar programs in the region?
Not in this case. So this was, again, for a specific case in Rhode Island. One could imagine that you could co-optimize to be able to provide kind of capacity services and therefore kind of tap into capacity payments as well, but not in the analysis that we did here did not.
Okay, thank you. A couple of people have asked about the parameters of the discussion. So one person says, the discussion so far focuses solely on bulk power exports and potential violations. Did your study look at using smart inverter capabilities to address voltage violations with VAR injection / absorption so that you need less storage? Another person asks whether you looked at more smaller sort of behind the meter. Is this all bulk wholesale, or are we looking at other types of PV and storage uses?
I can take that one. We did have a scenario that was looking at smart inverter controls. In fact, the only reason that we looked at one that was not was just out of curiosity to see what the impact of the smart inverter controls was. But we do understand that there are standards for using smart inverter controls, and those were applied in the analysis. As for behind the meter systems, no, we did not include those. This analysis was limited to front of the customer meter systems that are not associated with a load.
And just to add to that, right? So, you know, we get applicants that can, you know, have smart inverter functionality, and you know, the utilities are adopting that smart inverter functionality across the United States in different, you know, sort of time schedules and so forth. But you know, this OEA concept goes well beyond the, you know, the possible capabilities of the smart inverters, right? So, you know, in lots of specific cases, we have $1 million investments that would never be mitigated by smart inverter functions, right? So this OEA investment, you know, you could think almost voltage is part of it, but there's also loading implications, there's flicker implications. So, you know, so smart inverter can help, but, you know, this OEA goes, I think, a bit further than the possible solutions that smart inverters can offer.
Okay, great. Here's a question about finance. The person says, there seems to be a variety of finance risk challenges likely to be more difficult to overcome with the involvement of OEAs. Debt and equity providers currently have high expectations for financial certainty, hence the heavy reliance on PPAs and swaps. How have your finance contacts gotten comfortable with these concepts? And are there signals that the risk-averse finance world will embrace this?
Those are all really great questions. I will say we haven't talked to any finance stakeholders specifically. If you are one, please contact us. Let us know how this resonates with you. I don't have any other response other than that. Naeem, maybe you have some words to say on that?
I mean, the only comment there would be that storage provides a little bit more flexibility on uncertainty in future wholesale market price profiles and trends. So adding a storage rather than just curtailing may provide a little buffering in terms of risk reduction. So that's the only comment I would make there. But I think it would be quite interesting to understand how how a financial stakeholder may interpret or adopt or be interested or not in the OEA.
Yeah, and if I may just add one other thing to that too. In thinking about that heat map, right, and then the following slide after it that showed the matrix of complexity that you might have in an operating envelope agreement, I think that that's really built to be flexible around what developers and what the financial community needs to have that financial certainty. And that combined with the fact that the OEA will be the default unless both parties mutually agree to a change in that OEA, we're hopeful that that will also be key to providing financial certainty.
And can we go to slide 22? It's one of Naeem's slides. So looking at this slide, what we see happening many times is the applicant actually downsizes to the 1.32 megawatts, right? You know, I'm just using this example, right? So we see that the applicant often downsizes to the smaller size to avoid the system upgrade. And so, again, from a utility perspective, right, we don't have insight into the finances, but you can see from the blue bars, right, there's substantially lower revenue than any of the other options, right? So one of the things about the OEA is, can you get them into, where they can maintain a 3.3 megawatt system, and then, perhaps their finances are even more attractive, right? So that's the idea here, and so that's what we're actually seeing. We see the sites not proceed at 3.3 megawatts. We see them downsizing to avoid the upgrades.
Right. So the OEA is really intended to help to reduce risk and to ensure for both sides, right? And that includes reducing risk, financial risk for the investor or the system owner.
Right.
Yeah. Okay. Is the operating envelope agreement static? Somebody is asking, in other words, is it based on the available hosting capacity at the time of interconnection application, or is it dynamic based on real-time loading of the system? Or maybe those
the
are
idea
not
is that it's static, right? And I touched upon this in my presentation, right? It's static so that they have that financial certainty throughout their lifetime, whether it's 10 or 20 years or what have you. And yes, as a utility, there's some issues there, right? So the system does change. It would be nice if there was a way to make it dynamic and still give the developers that financial certainty, but I haven't figured it out. So, right. So,
next paper.
there could be some sort of opportunity in the future. And again, when we get a distributed energy resource management system, I think some of this goes away, and everybody just relies on the DERMS, which is a real-time dynamic system. But until then, we need something.
Okay. Can we get the slide up again with everyone's contact information? I think we have a questioner too who wants to know how to contact, presumably for a follow-up. And while we're doing that, somebody wants to know, is there a model agreement we can see and work from? So this is a good lead-in to where and how are these materials going to be available? Is it in a form anyone could actually start to use? And if not, what's the next step? And this is going to be the last question because we're a little over time here.
Yeah, absolutely. So going into this, we wanted to put together a model operating envelope agreement so that we could include it in our report. And we had so many questions. We wanted to get the report out first so that we had plenty of time to engage with stakeholders, to engage thoughtfully, conduct legal, regulatory discussions and reviews of these sorts of things. And so we opted to not include a model agreement in this report. However, it is our full intention that as we continue forward with these conversations, we hope to hear from other jurisdictions about who is actually implementing something like this so that we can highlight model agreements over there and sample agreements over there. And we hope to develop one ourselves as well as we continue these discussions here locally. So short answer, no, but we hope to have one in the future. So please contact us, SEIN@nrel, NREL.gov. Send that email. Joyce will get it. She'll pass it along to the entire team. We'll follow up with you. We'd love to talk more.
Great. And there's a report or 2 reports. Are those available?
There are indeed 2 reports. You can get to them through NREL's website, and they're also available at energy.ri.gov under resources.
Okay, great. Well, this has been excellent. Thank you so much to all of our presenters and those who participated. I apologize if we didn't get to everybody's questions, but we did our best. And Samantha, I think, maybe has a couple of upcoming events to mention that you might be interested in.
Thanks, Todd, and thank you to all of our speakers. That was really great. So to our audience, on our screen right now, you should see a list of some webinars that we have coming up in the next few weeks. Some really interesting topics that we will be covering, and you can read more and register for those at cisa.org/webinars. And as I mentioned at the beginning of the webinar, we did record this, and we are going to post a PDF of all of the slides. We'll get that up on our website probably tomorrow, and we'll also send you a follow-up email tomorrow with a link to those resources. So thank you again so much to all of our presenters. That was fabulous. Thank you to everyone who attended, and we hope to see you at the next one. Bye, everyone.
Thanks, everybody. Bye-bye.